So this is cap 32, and it's about the Carnot cycle. We need to find the work done in each step. So for example, from A to B, what is the work done? From B to C, C to D, and D to A. And then we need to find the change in internal energy and the overall heat added to the system. So in the Carnot cycle, the upper and lower legs, the temperature is constant. So from A to B, the temperature remains to be 300 kelvins, and from C to D the same, like the temperature is 289.13 kelvins. Since the temperature doesn't change, so this PV equals NKT. Since the temperature doesn't change, PV wouldn't change as well. So PV at point A and PV at point B should be the same. So PV at point A, it's 100 times 4, which is 400, and PV at point B is 80 times 5, which is also 400. The same applies to from C to D. Since there is no change in T, there shouldn't be any change in PV. So pressure times volume here and pressure times volume here, they're both they should be, I don't know, I need to calculate it, but it would be like 50 times 4.3, and this would be 40 times 5.3875. It will give you the same value for PV. Anyway, since this is at this steps from B to C, Q equals 0, change in Q equals 0, and here as well, change in Q equals 0, and our temperatures satisfy that value. You'll not be asked to construct like a Carnot cycle. Probably you'll be given all the necessary values, so you don't have to worry about your values being appropriate. So let's start finding the work done. So the work done from A to B, to find the work done, you don't need any calculations. You just need to be able to find the area under the curve. So what is the area under this curve from A to B? What you need to do is draw a rectangle. So if we draw a rectangle like this, we have this rectangle here, right? What is that rectangle? The area of that rectangle, it is 80, so 80 times, and this length is 1, right? This is 1 meter cubed, and this is 80. So 80 times 1 will give you 80 pascals times 1 meter cubed, plus we also have this triangle here. This triangle. So we also need to add the area of that triangle as well. So what is the area of the triangle? It's height times base divided by 2. So from A to B, so the area of the rectangle was 80, and the area of the triangle is, so this is 20 and the base is 1, so 20 times 1 divided by 2, that's the area of the triangle plus the area of the rectangle, which will give you 90. So the work done from A to B, it's 90, and since our volume is increasing, so the work done is pressure times change in volume. So if your volume final is bigger than your volume initial, in this case, in our case, it's volume final is bigger than volume initial, we'll have a positive work value. So this would be from A to B, we're doing positive work, so that's 90. We do the same thing to find the work done from B to C. So from B to C, we're just trying to find the area under that curve. So under this curve, we have this area, right? So we have this rectangle again, which is like 40 by 0, so 5.375 minus 5, 40 times, that's the height, and the base is 0.375. So that's what I wrote down here. From B to C, 40 times 0.35, and we have this triangle here. And what is the area of that triangle, like from B to C? That's again height times base divided by 2. What is our height? Well, it's here's 80, 40, our height is 40, and our base again 0.375. And you divide that by 2 because it's a triangle, and you should get like 22.5. Again, we are going from smaller volume to a larger volume. That's why our work done is positive. Work done from C to D, again, you do the same thing. But now we are going from like bigger volume to a smaller volume, from like 5.375 to 4.3. Again, we need to find the area under this curve, so we have this. So that is our area. And again, we have this rectangle, which is 40 by, like, you need to subtract 4.3 from 5.375. That will be your base, and your height is 40. So here, 40 times negative 1.075. Again, this is from like subtracting 5.35 from 4.3. That's, you're trying to find change in volume. That's negative because our final volume is this, so final minus initial, that will give you negative value. And our work done is negative because it's going the other way. And then plus our, and we have a triangle here. Our height of this triangle is 10, from 50 to 40, and the base of this triangle, it's again the 1.075, again it's negative, and divided by 2 because this is a triangle, and that should give you negative 22.5. No, that should give you negative 48.375. And then the work done from D to A, again you're trying to find the area from under this curve. So we have this right, and our rectangle is here from 50. So our height is 50 and our base is 0.3. So 50 times 0.3. Again, 0.3 should be negative because you're going from larger volume to smaller volume. And the area of this triangle is 50, from 100 to 50, it's 50. Our height and our base is again negative 0.3 divided by 2. That should give you the area of the triangle. And the work done from D to A is negative 22.5. Okay, so now let's try to find the change in internal energy. So change in internal energy from A to B, the formula for internal energy is 3R2 times N times K times delta T. From A to B, since there's no change in temperature, like we said in the beginning, from A to B there is no change, it's constant, it's 300 kelvins, it should give you 0. internal energy change from B to C, it's 3.302 times N times K times change in energy. 302 times, I took my N, it will be given to you, number of particles, I took it as 10 to the power of 23, times, this is our constant, this will be given, times change in temperature, our like final temperature is 289.13 kelvins, and our initial temperature is 300 kelvins, so the difference from B to C, it should give you negative 10.87 kelvins. And if you calculate it, so the internal change in internal energy give you negative 22.5 joules. From C to D, again, since there's no change in energy, change in temperature from C to D, it will be 0. Change in internal energy from T to A, again, 302 times number of particles times our constant, and again, change in energy. We're going from cold temperature to a little bit hot temperature, so our final temperature is 300 Kelvin from T to A, minus our initial temperature is this, so the difference should give you where was I? 10.87 kelvins. And so if you calculate this, change in internal energy from D to A should give you 22.5 joules. Now we need to find Q. We know that Q is, we need to find Q, energy added, for the entire cycle, not step by step, but I found it step by step, like, just so that you can see. So energy added from A to B, we just add the work done plus change in internal energy from A to B. So our work done from A to B was 90, and our change in internal energy was 0. So you just add up all the values that we found here. From B to C, Q should be 0, right? Like, that's kind of a rule for Carnot cycle. And we found work to be from B to C 22.5, and we found the internal energy to be negative 22.5, and that actually satisfies. When we add these, we get 0, so that satisfies the Carnot cycle. That's what Dave mentioned in class. When constructing this, we need to pay attention to this, but like I said, probably you will not be asked to construct any Carnot cycle. You'll be given all the necessary values. So you find the energy added in each step, and like from D to A, again, we get 0, but we're asked to find the energy added or the entire cycle. To do that, we just find the work or the entire cycle. So we add all the works in each step, and we got 41.625 joules, and change in internal energy, I got 0 when I added this value, that value, and this value, and that value. And at the end, you just add up the overall work plus the... So you just add the work plus U, or the entire cycle, and you should get Q. Here I think I found Q by adding all the steps. Either way is fine. You could also do Q over the cycle or the entire cycle equals work over the entire cycle plus U over entire cycle. They give you the same things. Okay, the last step, we need to find the efficiency. Efficiency is 1 minus Tlow divided by T high. So 1 minus Tlow, our temperature the low temperature was 289.13 kelvins divided by 300 kelvins, and you should get the efficiency of this. And that's it for this problem.